In our previous video, we talked about open and closed sets in the reals, and more generally in Rn. This is the beginning of the subject of point set topology, which is a very useful tool in analysis as well as in many other areas of mathematics. And a very good illustration of the use of these concepts is found in the definition of continuity. Here, I'm going to remind you the definition of continuity is given in any calculus textbook. This is for functions of one variable. And rather than talking about f being continuous at a single point a, I'm talking about a function which is continuous everywhere on its domain. So the variable a gets universally quantified here, along with several other quantifiers. So a function f from the reals to the reals is by definition continuous if for every real number a and every positive epsilon, there exists a positive delta such that for every x lying within delta of a, the value f of x lies within epsilon of f of a. This is the symbolic representation of the definition of continuity. You'll see that the definition starts with universal quantifiers for a and epsilon. Then there's an existential quantifier for delta, followed by another universal quantifier for x. These quantifiers can be moved to the front of the statement, but we need to keep them in this same order. As well as the quantifiers, this definition has other subtleties, including the arrows, the implication signs, not to mention the use of inequalities, which trip up many students who would prefer to be dealing with equalities. My point is that the definition of continuity as found in every calculus textbook is just unavoidably complicated. But as important as the concept of continuity is, sadly, we often shortchange our students by not giving even the definition in our calculus classes. And why? Well, our experience is that students don't manage to wrap their heads around this. Now, the full definition of continuity makes use of the definition of limit, but you'll see a slight simplification here from the full definition of a limit. In the portion that I've highlighted here in red, we would ordinarily require 0 less than absolute value of x minus a less than delta. But when defining continuity, the extra condition of 0 less than is unnecessary because the conclusion for f is going to be satisfied regardless in that case. So if x happens to equal a, the conclusion holds anyway. So there's no harm leaving out the 0 less than here. You should think about this point and convince yourself what I'm saying. For simplicity, I'll assume the function f is defined on the entire real line. Although for functions with other domains, especially a subset of the reals, this definition is easily modified and adaptable. In fact, this definition that I'm showing you here can be adapted to Rn or really any metric space. Now, so far, all I've managed to do is to remind you how complicated the definition of continuity is. Maybe this was already obvious to you. Now we can move on to our next point, which is how topology helps us to remedy this difficulty. Let's consider the general case of a function f mapping elements from a set x to a set y. Given any subset A of x, we speak of its image f of a, which is the set of all elements f of little a, for little a in capital A. Also, for any subset B of y, we talk about the preimage of B, which is the set of all elements of x that get mapped into B. So the preimage of B is a subset of x, while the image of A is a subset of y. Now, I'm definitely not saying that f inverse is a function here. Well, really, I'm not saying that f has to be invertible. F does not have to have an inverse function at all for what I'm saying to work. To be able to talk about images and preimages, you can do that for any function at all. Doesn't have to be a one-to-one function, doesn't have to be onto. In general, if you start with a subset B of Y, take its preimage, and then the image of that preimage, you won't necessarily get back to the same set B you started with. Instead, you get a subset of B. Similarly, if you start with a subset A of X, take its image and then take the preimage of that image, you won't get back to the same set A you started with. Instead, in general, what you'll get back is a superset of A, something containing A. But both of these properties that I'm showing you at the bottom of the screen, the subset relations here, they can be easily checked. You should stop the video now and think about these statements to convince yourself that they are true for very obvious reasons. It'll be easier for you to check them yourself than if you try to follow what I'm saying if I spell out the details in the way of proofs. Stop the video now and check these two statements at the bottom of the screen. By the way, if f happens to be invertible, meaning one-to-one and onto, then both of these subset relations at the bottom turn out to just become equality. Returning now to our calculus definition of continuity, let's paraphrase this using our language of the image of a set. To say that f is continuous means that for every point A in the domain and every positive epsilon, there's a positive delta such that f maps an open ball of radius delta centered at A into the ball of radius epsilon centered at f of A. In other words, if you take any positive epsilon at any point A in the domain, there's a small ball around A whose image under f is contained in the epsilon ball around f of A. Points close to A get mapped to points close to f of A. Now we are ready to smooth out this definition of continuity even more, using the language of topology. We prove that a function is continuous, in the Calc 1 sense, if and only if the preimage of every open set is open. You got to find it really remarkable that we have apparently simplified the definition of continuity so much, especially since we have stressed the importance of the multiple quantifiers in the definition and the need to keep them in the right order, and the subtlety of the implications and the use of inequalities. Given the many subtleties wrapped up in the definition of continuity, how is it possible to achieve this much apparent simplification? To say that a function is continuous, if and only if the preimage of every open set is open? Like, how did we boil it down from multiple quantifiers to just a single universal quantifier? Where did all the other quantifiers go? Well, all the quantifiers are still there, implicitly. The quantifiers are now wrapped up inside the definition of open set and the definition of preimage. This is something like the way a computer programmer uses subroutines. If you're familiar with computer programming, a subroutine hides all the technical details from some part of the computation, so you don't have to look at all the inner workings of the subroutine every time you call that subroutine by name. Out of sight, out of mind, right? Using subroutines helps you to focus on the higher level reasoning in the main routine, focused on the forest instead of the trees. So it is in analysis. We use topology to sweep some of the more tedious details under the rug, so we can keep our eyes on the bigger picture. So if topology can streamline our thinking so much, in particular, if the definition of continuity really looks this much simpler, why didn't they teach us this definition in calculus instead of the epsilon delta definition that's there in the calculus book and all the quantifiers that go with it? Well, for one thing, in order to be able to use this streamlined definition of continuity, You still have to understand a few concepts, including images and preimages, what it means to be open, and basic properties of open sets. Moreover, the epsilon delta definition of continuity, given in Calc 1, is directly motivated by the graph. That's not so much true for the boiled-down version, where it really takes some more mathematical maturity to be able to use this criterion for continuity, to use it effectively. Also, our purpose in analysis is different than in Calc 1. The topological criterion for continuity, that preimages of open sets are open, is exceptionally useful for writing short proofs of theorems that would have been very tedious using the epsilon delta criterion. This suits our purposes in analysis, where our goal is to write proofs of theorems. In calculus, our goal was very different. There, the closest we came to a proof would be asking a student, given a function f and a point A, and given a positive number epsilon, find the right delta that works for that particular epsilon. The original definition of continuity would have been much more appropriate for that kind of exercise. Enough prevaricating, let's do a proof of this theorem. This is an if and only if statement. I'll take the forwards direction first. So we assume that f is continuous by the Calc 1 definition. And let V be an open subset of the reals. We need to show that the preimage of V is open. Let A be any point in the preimage of V, which is to say that f of A is in V. This is saying that the preimage of V is non-empty, but of course if the preimage of V were empty, then f inverse of V would be open anyway, and we'd be done in that case. Since V is open, there exists a positive epsilon ball, centered at f of A, which is entirely contained in V. By the epsilon delta definition of continuity, there's a delta ball around A, which is mapped entirely into the epsilon ball around f of A, which again is contained in V. So, by definition, the delta ball centered at A is contained in the preimage of V. This shows, by definition, that the preimage of V is open. We just showed that the preimage of every open set is open. This proves the theorem in the forward direction. Now, for the converse, suppose that the preimage of every open set is open. Let A be any point in the domain, and let epsilon be positive. Consider the epsilon ball around f of A. This is an open set containing f of A, so its preimage is an open set containing A. So by definition of open, there exists a positive delta such that the delta ball centered at A is contained in this preimage. By definition, this means that the image of the delta ball centered at A is contained in the epsilon ball centered at f of A, which is exactly the requirement of the Calc 1 definition of continuity. This completes the proof of the theorem in both directions. An easy fact is that the composite of continuous functions is again continuous. This is not hard to prove, really, using the Calc 1 definition with epsilons and deltas, but using the topological definition, you can prove this in even less time. Like, it's as easy as reaching over in the morning to turn off your alarm clock, I'd say. Suppose f is a continuous function from x to y, and g is a continuous function from y to z. So g composed with f is a function from x to z. Now for every open subset u of z, its preimage under g is open in y, and the preimage of that under f is open in x. This says exactly the same thing as the preimage of u under g composed with f is open in x. QED. Now, we're ready to say what point set topology is in general. This is the axiomatic viewpoint where we say anything satisfying certain axioms is a topology. We've mentioned other axiomatic systems before. We've talked about the Zermelo-Fraenkel axioms for modern set theory. Actually, they're too complicated to write them all down. I have mentioned the axiom of choice, but not the other axioms in general. We have introduced here axioms for the real number system, which are still somewhat complicated, but they're very important for doing analysis. Also, I have listed the axioms for general ring theory and field theory, axioms from algebra. This was much easier. The axioms for point set topology, by comparison, are about the simplest axioms you can find. I mean, considering how useful point set topology is, it's hard to find anything like topology where such a simple set of axioms give you something so useful. Here are the conditions for topology. Let X be any set. A topology on X is a collection, call it script T, a collection of subsets of X satisfying three basic properties. First of all, we need the empty set and X itself to be in our collection, script T. Also, given arbitrary elements U sub I in our collection, we need their union to also be one of the sets in our collection. Finally, if you intersect finitely many sets that are in script T, again you get a set in script T. Assuming these properties are satisfied by a set X and a collection, script T, of subsets of X, we call script T a topology on X. Sets in script T are called the open sets, and X, together with script T, is called a topological space. The point here is that the same set X can have more than one choice of topology, script T. So, depending which topology you choose, you get different choices of topological space. So we refer to the pair X together with script T as a topological space. But if the choice of topology, the script T, if it's clearly identified from context, then we can be lazy and just refer to X as the topological space. Important examples for us will be where X is a set of real numbers, or possibly a subset of the real numbers, usually the domain of some function. In these cases, our choice of topology will be what we call the standard topology, where open sets in the reals, for example, will be the unions of open intervals. If X is a subset of the reals, just intersect X with the open sets of the reals to get the open sets of X. More on that later. Now, let X and Y be topological spaces. We have some topology T1 for X and some topology T2 for Y. Just think of these as subsets of the reals with the standard topology in each case. A function from X to Y is said to be continuous if the preimage of every open set of Y is open in X. This is the general definition of continuity. It generalizes the definition from Calc 1 to a much broader context. To say that a space X is connected means, by definition, that its only clopin sets are the empty set and X itself. Again, clopin means both open and closed. Closed set is one whose complement is open. In other words, X is disconnected if and only if it can be partitioned into two disjoint, non-empty, open sets. In the previous video, we talked about why these two last statements here are saying the same thing. Suppose that the set X has a metric, also known as a distance function. We have talked before about what this means. Recall that a distance function, d, assigns to any pair of points x and y a non-negative distance d of x and y. It's the distance from x to y. We require that d of yx is d of xy. And we require the distance from x to y is strictly positive unless x equals y. Also, it is crucial that d satisfy the triangle inequality. If the set X has a metric d, then this defines a topology on X called the metric topology, in which the open sets are simply the arbitrary unions of open balls, just like in the reals or in Rn. So every metric defines a topology, and not the other way around. There are some topologies that are not defined by any metric. Metric topologies is really just a special case, an example of a class of topologies. If X is any subset of the reals, then the distance function on the reals restricts to a metric on X. This gives us the corresponding topology on X. With this understanding, the open sets in X would simply be the intersections of X with the open sets in the reals, as I've previously mentioned. For example, the rationals form a topological space using the usual metric topology. This space is not connected, since the rationals can be partitioned into two open sets U and V, as shown. The sets U and V are not open in the reals. However, in the context of our topological space Q, the rationals, they are open. This is a subtle point here to watch out for. Here is the general setting for the process we have been describing. Let X be any topological space with script T as its topology, and thus the collection of all open sets in X. Then every subset A naturally inherits a topology whose open sets are just the intersections of A with the open sets on X. The closed sets on A are just the intersections of A with the closed sets in X. We call A a subspace of X. And this topology for A is the subspace topology. Now, the word subspace here has nothing to do with subspaces in linear algebra. Here we're talking about topological subspaces, a different idea. So it's in this sense that Q is a subspace of the reals. Here we have a subset of the rationals, which we call U, which is neither open nor closed in the reals, but it's both open and closed in the rationals. It's open in the rationals because it's the intersection of the rationals with an open interval. It's also closed in the rationals because it's the intersection of the rationals with a closed interval. Similarly, a couple more examples. Let's look at the closed interval 0, 1 here as an example of a topological space. It's a subspace of the reals. In this space, the interval bracket 0 to 1/2 right parenthesis, that's an open subset of the closed interval 0, 1, because it's the intersection of our space bracket 0, 1 with an open interval in the reals. The closed interval 0 up to 1/2 is closed both in the reals and in bracket 0, 1. Well, it's the intersection of bracket 0, 1 with a closed interval of the reals. The most basic notions in topology are that of an open set and a closed set. We have also introduced connectedness and continuity, both of which are topological terms defined using open sets. No surprise, therefore, that we can easily prove lots of other things using the basic language of topology. For example, here we show that a continuous image of a connected set is connected. This is to be expected. If we continuously transform X, then we're not allowed to break it apart into two or more pieces. Let's actually prove the theorem here. We take a continuous function f from x to y. I'll want f to be onto, which is to say surjective. This is just a way of saying that y is actually the image of x under the function f. We assume that x is connected, and we have to prove that y is connected. We argue by contradiction. If y is disconnected, then y is partitioned as a disjoint union of two non-empty open sets U and V. Since x is the preimage of y, it is a disjoint union of the preimage of u and the preimage of v. This just says that every point of x maps into either u or v, not both. Since u is non-empty and f is onto, something has to map into u. So the preimage of u is non-empty. Similarly, the preimage of v is non-empty. And both of these preimages are open, since they're preimages of open sets. Wait a minute, this cannot happen, since x is connected. This gives us the desired contradiction, and that proves the theorem. Now, in the previous video, we've shown that the real line is connected, and from this it's easy to show that every interval in the reals is connected. This is an easy corollary of the previous theorem. For example, here is a continuous surjection from the reals to the closed interval 0, 1. Since the real line is connected, the previous theorem shows that the closed interval 0, 1 is connected. Similarly, every interval in the reals is expressible as a continuous image of the reals, so every interval is connected. I have to say that this is what is important about intervals, is that they're connected. There's an if and only if statement. Connected subsets of the reals are intervals, right? A subset of the reals is connected if and only if it is an interval. Now we're finally ready to prove the intermediate value theorem. We show that if a continuous function from closed interval AB to the reals is negative at one endpoint and positive at the other endpoint, then at some interior point between A and B, f must attain the value 0. We never proved this in a calculus course. We could have proved it in our course weeks ago, but at that time, the best proof we could have offered would have been a fairly ugly and tedious proof. Now, we have the tools and the language of topology. We can write a much more succinct and clear proof that conveys exactly the essential ideas of what's going on here. Our proof is by contradiction. Suppose that the function f is never 0, so that means that f of x has values in the negatives union the positives, which is excluding 0. That is, f gives a continuous function from the closed interval AB to the union of the negative reals and the positive reals. Then the image of closed interval AB under f is partitioned into the negative part, which we call u, and the positive part, which we call v. Both u and v are non-empty, since u contains f of a and v contains f of b. And both u and v are open subsets of the image, because they are the intersections of f of ab with certain open intervals in the reals. Here we refer to the subspace topology for the image f of ab. This exactly says that the image f of the interval AB is disconnected. On the other hand, the domain closed interval AB is connected, since it's an interval in the real line. So here we have a contradiction. This is a very short proof of the intermediate value theorem.